Alright, welcome back everybody, and today we're going to be taking a look at this integral right here, the improper integral from negative infinity to infinity of the cosine of x over cosh of x. So this one's quite an interesting one. It has trig and hyperbolic trig inside of it. Along the way we're going to be actually coming across an integral that I've already evaluated before, namely the integral from 0 to infinity of x to the n over x plus 1 dx, and you can check the link down in the description below or probably up here somewhere, but this integral actually nicely evaluates to minus pi over the sine of pi times n. So we're going to be encountering this integral along the way while we solve this thing, which is pretty cool. And just one more note, n is actually between -1 and 0. In the case of this integral, we're actually going to be taking a look at the real part. So this actually works for the real part of n being between -1 and 0. Alright, so let's go back to this integral now, and what exactly can we do? Well, at first I want to rewrite cosine and cosh, because in the form they're in now, we can't really do much with it. I want to rewrite it in terms of some exponentials, which are a little bit nicer to work with. And we actually know the complex exponential definition for our cosine right here, and, well, the actual exponential definition for the hyperbolic cosine. So we can actually rewrite this as integral from negative infinity to infinity. Cosine of x, we know that's exactly e to the ix plus e to the minus ix, all divided by 2, and then all of this is over, so this is our cosine right here, over our cosh, and our cosh is e to the x plus e to the minus x over 2. Alright, and now, nice thing, we have a common factor of a half on the top and the bottom. Cancel out those halves there, so now we have the integral from negative infinity to infinity of e to the ix plus e to the minus ix, all that divided by e to the x plus e to the minus x dx, like so. And we have this expression now. Doesn't look too nice, but we can actually do a little bit of a simplification right here, because notice on the bottom we have two exponentials, and ideally we would just like one, because we're actually going to be using a substitution later on. So in order to get one exponential on the bottom right here, what I'm going to do is I'm going to multiply the top and the bottom by e to the x, and what that's going to do is it's going to cancel out with this exponential term right here. So if we multiply the top and bottom by e to the x, so all of this we're actually going to multiply by e to the x over e to the x, still have our dx like so. Now we have the integral from negative infinity to infinity. If we distribute on the numerator right here, we're going to get e, we have a common factor of x on top. So when you multiply two exponentials together, the arguments actually add up. So we have I times x plus I, and that's going to give us, well, a common factor of x right here. And then we have 1 plus I. So 1 plus I in here. And then if we do the same deal on the second exponential, we're going to get plus e to the x, and then we have 1 minus I. So we have 1 e to the x, and then a minus I right here. Alright, so that's the numerator done. How about the denominator? We're going to have e to the 2x right here. And then notice e to the x and e to the negative x is going to cancel out, giving us 1, and that was exactly what we wanted. Now we only have one exponential on the denominator. Now we can do a substitution. Initially, when I first did this integral, actually, I thought it would be nice if we could substitute this whole entire thing. But I realized if we only substitute just this e to the 2x term, we can actually turn this integral into this integral that I have up here, which is in the form x to the n over x plus 1. So we kind of already have our x right here. We're going to have an x plus 1. Okay, so let's actually do our substitution right now. So now we're going to let's choose a new variable. I really don't know. Let's choose t be equal to e to the 2x. So e to the 2x like so. That means that our dt is equal to, our differentiating this thing, we're going to get 2 times e to the 2x dx. So some basic chain rule stuff there. And, well, where can we go from here? Notice that on the numerator right here we have two exponentials, and we can actually see this as e to the x but raised to the 1 plus I, and e to the x raised to the 1 minus I. So it would actually be nice if we could get some kind of expression for our e to the x. And we can actually do it directly from here just by taking the square root on both sides. So raising both sides to the 1/2 power, we're going to get t to the 1/2 being equal to e to the x. Alright, so now we know what our e to the x is. It's exactly t to the 1/2. And I think that should be everything. And also one more thing right here. This e to the 2x, that's exactly our t. So dt is actually also 2 times t dx, which means that our dx is equal to 1 over 2t dt, like so. Now we can plug everything back in. So now this integral is equal to the integral from minus infinity to infinity of e to the x, which is exactly, what was that? E to the x was t to the 1/2. The bounds are actually going to change, I forgot about that. If we plug negative infinity into this e to the 2x, we're going to approach 0. And if we plug infinity into there, well, it's just going to blow up, giving us infinity. So now our e to the x, that was t to the 1/2, so we have t to the 1 over 2, and that is raised to the 1 plus I, and we can just multiply it directly in, so 1 plus I like so. And we're going to have plus e to the x again is t to the 1/2 raised to the 1 minus I. And let's see, what else do we have? We have our e to the 2x right here. That's exactly our t, our substitution, so t. And then we have this plus 1 still. And how about our dx right here? Well, our dx turns into 1 over 2t dt. I'm going to bring a 1/2 out to the outside, like so. And then 1 over t dt. Alright, so this is what we have so far. Let's erase this substitution. We don't really need it anymore. Where can we go from here? Well, we have this 1 over t right here. We can actually simplify it or cancel some things out with the numerator right here. Because notice that 1 over t, that is exactly t to the minus 1. So we're pretty much multiplying this numerator right here by t to the minus 1. All of this stuff right here. And, well, we have the same base right here. And all we need to do is add the exponents together. So now if we keep going, we have that this is equal to 1/2 times the integral from 0 to infinity of, notice right here, we have the real part right here as being 1/2, and we're subtracting 1. So 1/2 minus 1, that's minus 1/2. So in fact, what we end up getting is t to the 1/2, and then minus 1 plus I. Because if you kind of expand things out here, you're going to get the real part as negative 1/2. And same deal on the second thing right here. Let's actually split up the integral a little bit as well. So we have 1/2 factor on the outside. We can split up the fraction, and then using the linear property of the integral to split those two fractions up. So now we have this part. This is all divided by t plus 1. That's all good, dt. Then we have plus the integral from 0 to infinity of, same deal over here, we have a real part of 1/2 right here. 1/2 minus 1, that's negative 1/2. So in fact here we're going to get t to the 1/2 and then minus 1 minus I, like so. All of this is divided through by t plus 1 dt and a big bracket, like so. Alright, so now notice that both of these integrals out here are actually in this form. We have our variable, for example, in this case it's t, so it's t to some power over t plus 1. So t to some power over t plus 1. And remember our restriction on n was that it had to be, well, the real part of n had to be between negative 1 and 0. And you can actually check right here, the real part is negative 1/2. The real part over here is also negative 1/2, so it is in between negative 1 and 0. So these two integrals are going to converge, meaning that we can use this formula right here. So what does this tell us? This tells us that this is equal to 1/2. This integral right here, that is, well, this is our n value right here. So this whole thing, that's our n, and same thing over here, this is our n value. So for this first integral right here, let's apply this formula. We're going to get minus pi over the sine of pi times n. So sine of pi, and this is our n value right here. So let's plug that in. So sine, I'm actually going to use the square brackets for sine just to differentiate it between the brackets inside just to make things easier. We have a factor over half right here, and then we have minus 1 plus I, like so. Alright, so that should be the first integral done, and now we have plus. This integral will evaluate to minus pi once again, over the sine, and now we have pi on 2, because of this factor of 2, and then we also have minus 1 minus I, like so, and not a set of big brackets. So this is what we have right now. Alright, this is looking pretty good. We can keep going from here. First of all, we can factor out a pi right here, and we can actually also expand out the insides right here. So let's actually do that on this line right here. We don't need this line anymore, so let's just get rid of it. So we've essentially already found the result right here. We've integrated and everything. We just need to clean things up because this actually has a real value. So first of all, we can factor out minus pi right here, so we have minus pi over 2, and then 1 over sine, let's expand out that bracket right there, so minus pi over 2, and then plus I times pi over 2. So that's our first fraction, and then we're going to add that with 1 over, we have sine of minus pi over 2 once again, and then we have minus I times pi over 2. Alright, so this is what we have so far. And now we can actually use the sine compound angle formula, and so we're going to get some pretty cool results out of that. If we have the sine of a plus b, for example, this can be written as, so this is the same as the sine of a times the cosine of b plus the cosine of a times the sine of b. So that's our sine compound angle formula. And notice, for example, let's take a look at this first fraction. Our a is minus pi over 2 and our b is I times pi over 2. So in fact, if we let a be equal to minus pi over 2 and b be equal to I times pi over 2, what are we going to get? Well, we're going to get sine of minus pi on 2, but sine of minus pi on 2, that's actually negative 1. So first of all, we have minus 1. Then cosine of b. Cosine of b, well, that's cosine of I times pi over 2. And there's actually this identity which relates the cosine and the hyperbolic cosine, namely that if you have the cosine of I times some real number x, for example, you can actually get rid of this I, but you have to turn the cosine into a cosh. So this is the same as cosh times x if x is a real number. So yeah, in this case right here, we're actually going to get cosh of pi on 2 because cosine of b, which is this thing right here, we don't want this I right here, so we're going to get rid of the I and turn the cosine into a cosh. So this is going to give us cosh of pi over 2, like so, and plus, well, cosine of a, cosine of minus pi over 2 is actually 0. So in fact, that whole second part right here, that actually goes to 0, which means that, let's see, this first fraction evaluates to minus cosh of pi over 2. So let's plug that in. We're going to get minus pi over 2, and then minus 1 over cosh of pi over 2. Alright, plus. And now, for the second fraction right here, the only difference is that, well, our b is negative. So that, if we let b equal to the negative version, so minus I times pi over 2, what are we going to get? We're going to end up with something familiar. This should be a cosh right here. So let's go through the working out again. Sine of a, that's sine of minus pi over 2, which is minus 1. Then cosine of b, well, just like before, we can use that identity, and we're going to get cosh, and we have a negative right here, but cosh is actually an even function, which means that cosh of the negative numbers is the same as the positive version, so this is the same as cosh of pi over 2. And then same deal again over here, cosine of a, cosine of minus pi over 2 is 0, so that whole second part actually cancels out to 0. So this is going to leave us with minus 1 over cosh of pi over 2. Okay, and we can factor out -1 on top and actually cancel it with this negative pi right here. So if we do that, we're going to get pi over 2. And then, let's see, we have 1 over cosh of pi over 2 plus another 1 over cosh of pi over 2. We have 2 of the same thing, so we can just say it's 2 times, well, one of these. So 2 over cosh of pi over 2. And 12. This 2 and this 2 will cancel each other out, leaving us with the final answer of pi over the cosh of pi over 2. And that is the final result for today's video. If you want, you could also write it as pi times sesh of pi over 2, because sesh is just 1 over cosh. But yeah, I actually like this answer better because it kind of mirrors what we had at the very start with the cosine and the cosh. So yeah, that is all for this video. Hope you guys enjoyed it. Yeah, until next time, have a wonderful day, and I'll see everyone later. Bye bye.